So hopefully we now have an understanding of validity and how we measure validity and how we can compare tests. But validity is only one, perhaps the most important aspect of a test, but only one aspect of it. We also need to know is if that test was repeated, would you get the same results? And also, if that test is repeated by a different person or a different machine, would you get the same results? And this is known as intra-observer, i.e. between the same examiner, and inter-observer, between different examiners, reproducibility. There are a number of ways of measuring reproducibility, and this depends in part on the nature of the data you're being presented with. For continuous data, such as blood pressure, you would use a coefficient of variation to examine reproducibility. You can also use interclass correlations, again, to measure how much agreement you have between the measures, and I will come back to interclass correlations in a moment. You do see that people use paired t-tests, but actually this is an inappropriate measure to actually measure agreement, because there may be a difference in the means because of a huge scatter in your readings, and therefore you may not get a statistically different result despite the fact your readings are very varied. Similarly, people use correlations, but correlation does not show you agree, it just means you're going in the same way. So for example, if I was to measure arch width in children, I could be getting a very different result from another examiner, but provided our examinations, when I measured, it was larger than the last measurement, and the next examiner's measurement was larger, we would still be correlated, but we could be getting very different numbers. For categorical data, people usually use a statistic called Cohen's kappa, and this measures agreement beyond chance, because actually anyone measuring might get it right, and so you need to overcome the effects of chance. There's another statistic sometimes used called Dice's coincidence index, and I'm not going to talk about it in any detail. Again, you will see quite frequently people just use levels of agreement, and that's inappropriate because it doesn't actually allow for chance. And actually, if it's a 50-50 call on disease or health, actually by random chance half the time you may just get it right anyway. I said I'd come back to interclass correlations, and one of the issues with categorical data, and sticking to our example of caries diagnosis, our caries diagnosis laser machine gives a reading from 1 to 100. So that's continuous data, but then we interpret it as on a scale. So 0 to 5, for example, is enamel is sound, 5 to 10 is enamel caries, 10 to 20 outer dentine caries. So we turn it into categorical data. That may be appropriate, but what will happen if we use that scale I've just used? 0 to 5 is sound, so I do one reading and I get a reading of 4, so I classify it as sound. I do another reading and I get a reading of 6. I'm only 2 apart, but I will still, as far as the Cohen kappa is concerned, I've got no agreement. However, that is clearly better than if I did a reading of 4 and then the next reading I got was a reading of 15. So interclass correlations are a way of measuring the agreement in a device with a continuous set of readings, and whether you use Cohen's kappa to look at the categorical data or interclass correlations depends on you and the information you want to get across, but frequently people will present both. Here we see diagnostic validity and reliability presented together, and how you need both of them to have a good test. The first of the targets shows a very reliable reading. All the arrow shots are in the same corner around about 1 o'clock, but it's not particularly valid. It's hitting the target, but it's not anywhere near the bullseye. The second picture shows a very big scatter. So again, we have low validity. We are hitting the target, but it's very widespread, and similarly low validity because although hitting the target, we have none in the centre. The third target, again, not very reliable because the arrow shots are across the whole target, and again, very low validity because we have none in the centre. And finally, what we're aiming for is actually all our arrow hits right in the middle, so we're very reliable, and as that's the correct answer, also a very valid test. One crucial aspect of any study is that you actually have enough patients in the sample, or enough items of any kind in your sample to actually get valid results. This would almost seem self-evident, but it's amazing how often studies actually are underpowered or don't have a big enough sample. And that's not because people set out to do bad science, but it's because actually collecting samples is very difficult. Getting people in everyday life to sign up to your study can be difficult. Clinicians finding time to enlist patients can be difficult. And even anecdotally, quite common diseases, when you're actually looking to find a patient with them, just seem to disappear. Here we see the definition of a sample size calculation, which is also known as a power calculation. The power of a test is the probability that a study of a given size will detect a real difference of a given magnitude. And I'm going to explain what that actually means. Again, we're going to stick to caries diagnosis. And this is actually a real situation that happened to me a few years ago. I was involved in a study, and we were taking digital radiographs with the type of film sensor that goes in the mouth and has a cable coming out to a computer to take your reading. We had 2 sensors and 1 cable, and we weren't getting any radiographs. So what wasn't functioning? Well, we knew the X-ray machine was working because we were able to use old-fashioned film to test it. So when we put either sensor in, we got no image. So we deduced that there must be a break in the cable, which is a frequent problem with the devices that have cables running into the mouth. So we sent the cable off and got a replacement, and 2 days later the new cable came, but yet our X-rays didn't work because in fact we had 2 broken sensors. And this is a very simple example of where we didn't have enough elements to test where the flaw was. At the very least we needed 1 more cable. So how in terms of your research do you do a power calculation? Because you can't just do an educated guess and say something like, well, I suppose 30 patients will be enough. The best way to do it is look for a study that has done a similar piece of research to the one you're involved with and use the data from that research. Of course, if you're in a very new area, you may not have that data available. In that case, ideally you would conduct a pilot study, i.e. a small study using the methodology you're going to use so that you can get the information you need on the prevalence of disease, disease progression, or whatever you need to inform your study. The next, and one of the most tricky things in a power calculation, is actually to decide what's a significant clinical change. So it was perhaps a new fluoride agent, you need to decide whether actually reducing caries by 1% would be clinically significant, or whether you would want a 10% reduction or a 50% reduction. And that is actually an educated guess that the research team have to come to, drawn on the available data and their knowledge. You then have to decide both your level of statistical significance, whether that's 0.05 or 0.01. You then have to choose the statistical significance that you're going to use, i.e. 0.01 or 0.05, and also the power that your study is going to have to actually detect that difference, i.e. the chance that if there is a difference it will be detected. And hopefully talking through how you do the calculation will make this easier to understand. So I'm going to use an example. You develop a new supplement to promote growth in 5-year-old children. Obviously there are a number of ethical issues around this, but it's a nice simple example. You know that children at age 5 grow 5 centimetres a year with a standard deviation of 2 centimetres. You and your colleagues think about it and decide that actually if you increase growth by 0.5 of a centimetre a year, that would be clinically significant. You decide that the probability of detecting the difference, you want a power of 90%. So you want to be 90% sure that if there is a difference, you will detect it. And you decide your significance level will be 0.05. Then, a nonogram is a graph which you're about to see in the next slide, which you can use for calculating power. You need to collect the standardised difference. And don't let this terminology frighten you. It's a target difference, i.e. what you've decided is clinically significant, in this case 0.5 centimetres, over the standard deviation, which we already knew was 2 centimetres. And therefore we get a standard difference of 0.25. And this is the nonogram drawn from Altman's book on statistics. What we see here is a standardised difference, and we had already calculated that to be 0.25, and then on the other side of the graph we have the power, and we had decided we'd have it at 0.9, which is the pink line. You then draw a line linking your standardised difference to the power you've decided you want, and where that cuts the lines down the middle tells you your sample size. And here you can see the upper line is at a statistical significance level of 0.05 and the lower line is at a statistical significance level of 0.01. In my example here, that means that we need a sample of 900 children. That's 450 in the experiment group and 450 in the control group. If, for example, we were to decide that we wanted a lower power, a power of 0.8, and then again drew a line from the standardised difference of 0.25, we can see that the number needed to achieve this power would be lower at 700 or 350 per group. And if you take some time and look at this graph, you can see how altering your power or altering your level of statistical significance that you've chosen alters the sample size you need. And which level of significance you take and which power you take, again, is something the research team have to discuss and decide on, but normally power is never less than 0.8. This diagram, I think, shows the thought process behind power calculations very well, but in fact most statisticians don't use the nonogram but actually use a formula to calculate the power. But this is what's behind the process.